Okay, we will start now. So this is the extra session that we have, and mostly what we do is we'll try to solve some problems. Okay, so let me recall the Silo theorems, which is supposed to be there in the eighth uh, week, but I just state the theorems, and then we may use it little bit. So first just recall some definition. So a group of order P power alpha, suppose if we have a group G, and if it has a order P power alpha, then we call this group as a P group. Okay. And let's say if you have another group here, okay, so you have a group which whose order is P power alpha times m. Okay. But what is the relation here is this P does not divides the. Suppose this P does not divide CM. Okay. Then this group of so then this is subgroup. This is called Silo P subgroup. Okay. And what we do is the number of Silo P subgroups we denote by NP. This denotes the number of Silo P subgroup. Okay. And call this one with this symbol Silo P of G. This is the set of all the Silo P subgroups. It's just a notation. Okay. So the Silo theorems deals with this particular kind of groups. Okay. Then okay, I didn't write it properly. Then the subgroup of order. So suppose you have a group here, which see you have this group. You write it in terms of the prime factorization. So when you write like this, suppose you can write it as P power alpha times m, where this P is a prime here, and it does not divide this m. Okay. Then if there is a subgroup of order P power alpha, we call that subgroup as a Silo P subgroup. So it is the subgroup. It's a subgroup which has the maximum P power order here inside this group. Okay. So this what the Silo theorem says is whether this kind of subgroup exists or not, and if suppose the subgroup exists, and what more you can say about this. Okay. So there are the three Silo theorems. So most of the time the proof is not actually very important. What actually important is the statements. Of course, the proof techniques are useful, but the statement of the theorem is more useful. So at least try to remember the statements. Okay, so Silo theorems. Okay, so the first theorem. So there are basically Silo theorem. I'm going to write it in 3 points here, 1, 2, 3. But this is the first theorem. This is the second theorem. This is the third theorem. Okay, so the first theorem says that Silo P subgroup exists. Okay, so this is important because in general, the converse of the Lagrange theorem is not true. For example, if you have a, let's say your kernel of G is n, and suppose if D divides N, that does not exist a group of order D. But what it says here is here this P power alpha, divides the order of G, and this theorem says that such a subgroup exists. And the second thing is if P is a CeLO P subgroup, so we have one subgroup is a CeLO P subgroup, and you take any other P group, P subgroup of G. So then the CeLO second theorem says, so there exists element G in G, such that you can say how this things looks like. It says that this Q is contained in a G P G inverse. Okay. So in general, if you take any other
Sir, Q subgroup.
yeah,
Q is any Q subgroup
Q is
or
a
P
P
subgroup?
subgroup. P subgroup, the same P.
Both are P.
Yeah, both are the same prime.
Okay.
Yeah. So it only deals with one standard prime. So basically, you fix the prime, and then the theorem states for the prime. Okay. So maybe probably I'll write it here properly. Let G be a group of order P power alpha times M, and so probably we'll write here where this P is a prime with P does not divides alpha. Sorry, P does not divides M. Okay. Under that hypothesis, you have the CeLO P subgroup exist, and if P is a CeLO P subgroup and Q is any P subgroup means so this is the definition of P group. So P subgroup means any subgroup of G which has prime power order. Okay, it need not to be that maximum prime power. It can be any even smaller prime power. So what it says is this Q will be contained in some conjugates of P. Okay. In particular, if you take this Q also as a CeLO P subgroup, this will be equal to QP Q inverse. So in that sense, if you take any CeLO P subgroup, they are all conjugate. Okay. So in particular, okay. And the third CeLO theorem deals with the number of CeLO P subgroup. So it says that the number of so it says the number of CeLO P subgroup is of this particular form. 1 plus Kp. So that is if you want to write it, you can write it using the congruence also. Np congruent to write it as 1 mod P. Okay. And also it has to satisfy another property further. Further, you have another property that Np divides this M. So where M is here, it comes from here. So we will group as order P power alpha times M, right? So that particular M. So this NP is congruent to 1 mod P and it divides the M. Okay. So actually you can say it a little bit general, but I kind of skip it. Usually we may not use it most of the time, so I'm not writing it. So here we are writing this NP divides M, right? You can write it a little bit more generally. You can write it as NP divides this normalizer G of P. You can write like this. Okay. So NP divides the size of the normalizer. Or maybe I will just give me a minute. I will see here. In fact, you can write it as NP is the index of the normalizer. You can write. So it is G index normalizer G of P. Okay. So, but this statement we won't usually use it. So I'm not unless unless you know the group, then you can compute the normalizer. Otherwise, computing the normalizer is not easy. So in that sense, we won't usually use that. So this this statement is a consequence of whatever we have it, but it is enough to most of the time it is enough to remember just this one. So I will just recall the statements again, and then we will move on to the problems. Okay. So again, just to recall it completely, a group of order P for alpha is called a P group, and if your group has a order P for alpha times M, where this P is a prime, and if this P does not divide M, okay, then any subgroup of this P for alpha of order P for alpha is called a CeLO P subgroup. And the number of CeLO P subgroup we use, let's denote it by N of P. Then we have the CeLO theorem. There are three statements in the theorem, or you can also say it CeLO first theorem. So this is called first theorem, this is second theorem, and this is the another one is the third theorem. Okay. But I'll just put it as a single statement, so a single theorem. It says first theorem says the CeLO P subgroup always exists. So whatever the group is, the CeLO subgroup always exists. And the second thing says if you have a CeLO P subgroup here and any other P group, this P group will be contained in some conjugates of the CeLO subgroup. So in general, what happens is this Q need not be contained in the P, but it is contained in one of the conjugate. And you can see if you take a conjugate of a CeLO P subgroup, that is again a CeLO P subgroup. So in particular, what it says is any two CeLO subgroups are conjugate, because you take this Q as another CeLO subgroup, so you can say any two CeLO subgroups are conjugates. Okay, and the number of CeLO P subgroup, if you want to compute, there is a formula. It says, I mean, it's not exactly tells you what is the number, but it says, okay, these are the possible restriction it gives. So it cannot be anything, but it has to satisfy these two conditions. One is that NP is congruent to 1 mod P, and the NP has to divide the M. Okay, we'll keep it in mind, and let's go and try the problems here. So last time we dealt with some class equations, right? So probably I'm not sure if I have to recall the class equation, but at least I will write what is a class equation. So if you have a group G here, and it acts on itself by conjugation, and then what you do is this action is the conjugation. If you look at the conjugation, this is the action, right? So it kind of splits so you see it as a set here, and this group acts on G. Okay. Now what happens is the orbits under this action partition this group G. Okay. And then if you write it using the orbit stabilizer, you will get a formula for the size, which is called the class equation. So you have the cardinality of G. This is basically the cardinality of center of G plus summation I equal to 1 to R. And you have the R bits here, so which will be, I think, G by centralized G of G. So I will tell what is this GA is and all. Or maybe I might have written it in the last lecture, so probably I will just scroll through it and maybe you can do it quickly. Sorry about the scrolling. But yeah, I should have written somewhere here. So yeah, here I have. So what you do is take G as a finite group, and G1 to G are the representatives of, you take it as a representative of distinct conjugacy class of G. Okay, and none of this conjugacy class should be contained in the center. Okay, then what you can do is you can write the cardinality of G as cardinality of center of G plus the summation of from I equal to 1 to R, where R is the number of representatives of the distinct conjugacy class. Okay, and here you have the index G upon the centralizer of Gi. And this equation is called the class equation. Last time we have used this to do some problems. This time, and we have seen there are certain equations are possible class equations and certain equations are not possible class equation. So here is a question which says that which of the following can be a class equation of finite groups? Okay, some of these can be a class equation, some of this cannot be a class equation. So let's do it. I have a lot of problems here. So let's do one by one. Okay, we'll copy paste here and we will do one by one. Okay, so let's start with this. So whether this is a class equation, that is a question, right? So your group has order 39. Okay, so which is basically 3 into some 13. Now, see, one thing what you can do is once you have this order of the group, the first thing that we can always do is to use the Silo theorems. So you can use Silo theorems and get what is the, see, you know that there is a subgroup of order 3, there's a subgroup of order 13, and you also know that the number of subgroups of order 3 and 13, right? So that is the first thing that we want to do. Okay. Just give me a minute. I will close the window. There is some noise there. Okay. That is what we are going to do. We are just going to first apply the Silo theorems. So let's compute the Silo theorems. So what we know is the Silo 3 subgroup exists, the Silo 13 subgroup exists. These two things we know. And let's find the number of so let's find the number of Silo 3 subgroups. See, not everything that we are going to compute is necessary, but let's just compute it. Okay. So what we know is this is congruent to 1 mod 3 and it has to divide 13, right? So what does this imply? This is congruent to 1 mod 3 means it can be either 1, 4, 7. So these are the numbers that are congruent to 1 mod 3. 10, I think, and then 13. Okay, so, and there are more numbers that are going, but it has to divide 13. So the only possible numbers here which divides 13 is either 1 or 13. The other number does not divide 13. Okay, so this much we have now. Now what about N13? See, N13 also we can do the same thing, right? So let's do the same thing, but I can tell you in some sense. Okay, anyway, see, although this is our ultimate aim, but I just want to compute everything about the Silo theorems, etc., so that we can have an idea how to compute these things. Okay, so this N13 is also congruent to 1 mod 13. So this will be either 1 uh, 13, sorry, not 13, 114, and then so on. Okay, and it has to divide 3, right? So the only possibility is N13 is 3. Sorry, not N13 3, N13 is 1. Okay. So now what we have computed is we have computed the Silo subgroup exists, and we have also said what is the number of Silo subgroup. Okay. Here we have the possibility for number of Silo 3 subgroup is either 1 or 3, and the possibility here is just 1. Okay. But now what we do is I will prove the same statement here. The number of Silo 3 subgroup is basically 1, but without using the Silo 13, Silo third subgroup. One can ask why on earth you are doing it again. But the thing is, I just want to illustrate there is a theorem that we did last time. So I just want to say one can use that theorem also and get it without using the Silo third theorem. So sometimes that will be helpful. That's why I just wants to do this. Probably will just show the theorem statement. I should have copy pasted it and instead I haven't done it. Sorry about that. So this was the main theorem for the left action that we did last time. Suppose if G is the finite group of order n, and P is the smallest prime dividing the cardinality of G. Okay. Then the statement says the any subgroup of index P is normal. So that is what it says. So if you have any subgroup of index P, then that subgroup must be normal, where P is the smallest prime dividing the cardinality of G. Okay, so let's see how we can use it here. This is not the one. Okay, so here we have. So if you look at this uh, Silo 13 subgroup, so let's look at. Let me write it as let's say P13. This is a Silo 13 subgroup. So what is the index of G by P13? So this is basically 39. So your group has order 39, and the P13 has order 13, of course, and this is 3. So this is the smallest prime that divides the order of the group. So by the previous theorem, what you get is that P13 is normal. So if your group is normal, then what you can say? Now let's look at the Silo second subgroup theorem. Okay. So the Silo second theorem says any two Silo subgroups are conjugates in G. Okay. So if you take any other Silo subgroup, let's say Q is a Silo 13 subgroup, then by the Silo second theorem, what we have? We have Q is equal to.
Conjugates.
Yeah, exactly. They are conjugates. This much we have. But what we have is here is the P13 is a normal. Okay. So what we get is Q equal to P. So what we have proved is the N13 is basically 1. Okay, so basically that is what we proved it. So there are many ways you can try these things. So I just showed you 2 ways to compute the N13. One is just directly use the Silo third theorem and you get. it's not guarantee always that you end up getting the number exactly. For example, in this case, what you get is you didn't get the number exactly. You get either 1 or 13. And sometimes what happens is both can be a possibility. Okay, because both of them gives a different groups. So both can be a possibility. So, but in the second method, what we did is we use that fact if you have a group such that if the index is the smallest prime dividing the cardinality of your group, then such a group has to be a normal. So that we used here. And then use the Silo-Second theorem, you will get the Q equal to P. That means all the Silo-13 subgroups are the same. Okay. So far we have N3 we have and N13 we have. Okay, but anyway, our ultimate aim is to compute whether this is a classic equation. But so far we have computed this. Okay, let's look at there are two possibilities here, right? 1 and 13. Let's analyze and see whether both can be a possibility. In some cases, both can be a possibility. In some other cases, both cannot be a possibility. But let's try to analyze here. So we have N3 is 1 or 13. Right. So let me write our group first here. So this is my group G, and I have identity element here. So my group has order 3 into 13, right? So by Lagrange theorem, if you take any element, it has order either a 3 or a 13 or 1 or 39, right? Okay. So if you have a group of order 39, then the group is cyclic, right? So the conjugacy, what is the classification for the cyclic group? So if you have something like Z39, that means what? This is a abelian group, right? So that means the center of this group Z39. So this is basically Z39 itself. So if you write the classification should be 1 plus 1 plus, etc. 139 times you just write it. So this is the classification. If you take a cyclic group. Okay, but we have some other classification, so we can, without loss of generality, assume that this group is not cyclic. Okay, if you assume it is not cyclic, then the only possible orders are 1, 3, 13. These are the only possible orders. Okay, so but what we have is N13 is 1. See, again, you see N13 is a cyclic group, and there is only one subgroup of order 13. Okay, in that subgroup of order 13, other than the identity, there is 12 elements here. Right? What are these elements? These are elements of order 13. Okay. This is, of course, identity, order 1 element. And let's look at what are the possible orders for this 3. I mean, element of order 3, let's see how many elements. Suppose if N3 is 1, then what happens? That means how many elements of order 2 will be there? There are 2 elements of order 2. Sorry, 2 elements of order 3. Why the other element is actually the identity, right? So we have only 2 elements of order 3. So that means there is 2. And that's all right. So because of the Lagrange theorem, and let's for now assume that it's not a cyclic group. So these are the only thing. That means let's compute what are the possibility here. So if you compute here you will be 12 plus 2, how many elements you get? So this is, I think, 14, 15, only 15 elements you have. But your group should have 39 elements, right? So I have only 15 elements I have. So this is not a possibility. This is not true, provided not cyclic. Not cyclic implies that N3 equal to 1 is not possible. So the 13 is the possibility. So if you have a 13, N3 is 13, that means there are 13 subgroup of order 3, right? So how many elements of order 3 will be there? Each subgroup here gives you 2 elements, right? So totally you will have 26 elements of order 3. So let's try to see how many we get here. So we have a 13 here and there's a 26 here. So total we get a 39 elements. Okay. So if you take a non-cyclic group, so this is a possibility. Okay. Let's say if you take the cyclic group, then what happens? So in the Z39, if you look here, you remember that fundamental theorem of cyclic group, right? It says that if you have a D divides 39, there is a unique subgroup of order D. Okay, it says there is a unique subgroup of order D. Okay, so that means the 3 divides the 39, so it means N3 is actually 1. So N3 equal to 1 is also a possibility. N3 equal to 13 is also a possibility. When it is a cyclic, it will be 1. When it is not cyclic, the possibility is 13. Okay. So in some sense, you can just write everything, these things together. Okay. So far we have computed a few things. So what we have seen is, if you look at this class equation cannot come from a cyclic group, and thus we can assume it is a non-cyclic. Okay. So we can assume the group is non-cyclic. In such a case, N3 is basically 13 and N13 is 1. So these are the things that so far we have done. So what we have done is N3 is 13 and N13 is 1. And your group is not cyclic. But in order to compute the class equation, what I need is this thing. I need to find what is the center, I need to find what is the centralizer, and then I have to compute these things. Right? So let's compute the center here. So what is the order of the group? Again, order of the group is 39. So what is the possible order for the center? The possible order for the center is 1, 3, 13 or 39. So, but this is not correct because of not cyclic. Okay. So the possibilities is one of these 3. Right. So let's see which are the following is possibility. Okay, let's do the cases. So let's say center of size of the center is 3. Then what happens if you look G by center? So G by center size will be 13, right? And this is a cyclic. So this implies G cyclic. Because any group of prime power order, so prime order is cyclic, not prime power order. Any group of prime order is cyclic. Okay, so G by Z is cyclic. So that implies G is abelian. See, this is not possible. If G is abelian, then what your class equation cannot be that one, right? So the question says, which is this class equation can be possible? That is what it says. Well, it may be possible or may not be possible. That is what it says. So we assume it is not a cyclic group. Then we say that 1 plus 1. I mean, if you take abelian group, the class equation will be 1 plus 1 plus, like everything has to be 1. So we can assume that it's not abelian group. So let me write it. Give me 1 minute. So this implies abelian, but our group is not abelian, right? So that means this is not possible. Okay, the center cannot have order 3. Similarly, you can do it, and you can say that center cannot have order 13 also. So these two orders are not possible. So what remains is the center of G order is just 1. Okay. So far what we have computed what is the center. We have also computed what is this numbers also. Okay. So this much we have computed so far. So what remains to compute is we need to compute the centralizers, and then we are done. So we have computed the size of the center of G, we have computed, and what remains is the size of the centralizers. So let's compute what are the size of centralizer. Suppose what are the possible orders here? The orders of possible order for X is either 1, 3 or 13, right? So because your group has ordered 3 into 13, so the order is 1, 3, 13 or 39, but we are assuming it's not a cyclic. So let's leave this and we have 1, 3 and 13, right? Suppose let's say order of X is 1. When order of X is 1 means it is in the center, so that also we don't have to worry about. Let's say order of X is 3. Okay. Now let's compute the centralizer. Okay. So what we know is the subgroup generated by this will be contained in the centralizer, right? So that means the cardinality of centralizer X should be at least greater than or equal to 3. But it has to divide, the cardinality of the centralizer has to divide 39. So the possible cardinality is either 3, 13 or 39. So these are the possible cardinality of the centralizer. Okay, because it is not 1 because this subgroup is here, but also here you observe that here use the Lagrange theorem. If you use the Lagrange theorem, what you get is 3 divides the cardinality of the centralizer of X, right? So that means the possibility is either a 3 or a 39. It cannot be 13 because 3 does not divide 13. So this is not possible. Why? Because 3 divides the cardinality of the centralizer. Okay, is 39 possible? Let's compute that. Suppose this is 39, that what does it mean? So 39 is what? It's the order of the group, right? So that means the centralizer this X, the centralizer G of X. So this implies the centralizer is actually G itself. So if the centralizer is G itself, that means this X belongs to the center of G. But we have seen that the center of G is actually equal to 1. That is not possible. Okay, so this is also not possible. So the possibility for the centralizer is actually only 3. So these are the possibility. We eliminated these two. So what remains is the possibility of the centralizer is just 3. Okay. So if you compute G by centralizer, okay, G by centralizer G of X, this will be 13. Okay. But how many elements I have of order 3? We have just written it here. We have 26 elements of order 3. So I will write here maybe. This is order 3. Okay. We have 26 element of order 3. And in each of the orbit, we have a 13 element, right? So this 26 element is split into a 13 element orbit. Okay, so probably I will write here. See, this is what? This is the size of the conjugacy class, right? So that 36 elements, it's split into 13 and 13 element conjugacy class. So if you draw a conjugacy class diagram here, so what happens is here you have 13 elements, and then here you have 13 elements. And of course, here you have this identity, there's just one element here you have. Okay, now so far we have accounted the element of order 1, the element of order 3 also we have take care of. So what remains is to compute the what happens with the element of order 13. So what is the element of order 13 here? So suppose x is a element of order 13, kernel of x is 13. So let's do the same thing again. We look at the centralizer g of x. The centralizer contains this subgroup generated by x. So this has a order at least greater than or equal to 13, right? I mean, I cannot write something like this. This is wrong. Okay. So 13 divides the order of the centralizer. So the possible orders are actually 1, 3, 13, and 39. But then this is not possible because 13 divides the centralizer. So these two are not possible. Only these two remains. If it is 39, do the same argument here. If the centralizer is 39, then the x belongs to center. But we have proved that center is identity. So that is also not possible. So the order for centralizer is basically 13. Okay. So what you do is use the Lagrange theorem. That's all. Use Lagrange theorem and and argue a little bit more, which I have said it, but I haven't write it down. And argue. So the centralizer order became 13 here. So if you compute G by the centralizer, so if you compute this order will be 39 by 13. So this will be 3. So how many elements of order 13 we have? We have 12 elements of order 13. So let's go back and see. Here we have 12 elements of order 13. And this 12 elements split into 4 conjugacy class, each of order 3. Okay. So maybe I'll write a conjugate diagram here. So this elements kind of split into 4 conjugacy class, each of order 3. Okay, so this is the class equation, and the class equation, if you write it, what you get is 1 plus 3 plus 3 plus 3 plus 3 plus 13 plus 13 equal to 13. Okay, so basically what we have proved is if G is non-abelian, so what we have proved is the following. If G is non-abelian, and order of G is 39, then the class equation is basically this one. Okay. So the rest of the problem, what you do is you do exactly similarly. So there are so many problems I have written it here. Some of them requires different ideas, but more or less you can do this way. Okay, so these 4 kind of goes similarly, because you see you can observe here. Maybe some of this may be different, but more or less it goes kind of the same. We see here, you can see here. These elements are all, this is what? This is 3 times 13. This is also 2 times 7. This is 3 times 7, right? 7 3s are 21, right? Yeah, this is 3 times 5. Okay. So these things are kind of similar. So all these things kind of goes similarly. But what I will, but let's, we have done so much. Maybe the next problem I will take this one rather than doing the same thing again. But I will just show a little bit more here. See, although what we have proved is if you have a non-abelian group, and if your group has ordered this is the classification. What I will show is such a group does not exist. So basically, the group of non-abelian group of order 39 does not exist. So that is what I am going to prove now. So let me call it as a theorem maybe. Well, that does not uses the classification, but we can prove this. There is no non-abelian group of order 30. Well, but what happens is this is a possible classification. If there is a group, if there is a non-abelian group, then this must be its classification. So in that sense, this is a possible classification, but right now we will prove that there is no group of order 39. So how do you prove it here? No, wait. Oh, no. I think there is a group of order 39. Sorry. Yeah, there is a group of order 39. Okay. This statement is correct. Actually, there is a group of order 39, and it is true. But sorry about that. Sorry to make confusion. But if you look here, this problem is again similar, right? So these numbers are all 3 times 13. All of them are basically of the form p times q, right? So this is also like that, 3 times 5. Okay, but probably I will prove here there is no subgroup of there is no group of order 15. Uh, this I will prove maybe. There is no non-abelian group of order 15. These are all similar, but one can prove there is no subgroup of order 15. So this is true anyway. So let me prove this one. So let's do the same thing again. First, what we do is we compute the number of CeLO 5 subgroup, not the CeLO 3 subgroup, but CeLO 5 subgroup we compute. This is congruent to 1 mod 5. I'm using the CeLO third theorem, and it has to divide 3. Okay. So 1 mod 5 means what? It can be 1, or it can be 6 or something more, but it has to divide 3. That means n5 is basically 1. Because only 1 divides 3, right? 6 does not divide 3. 3 divides 6, but 6 does not divide 3. So the only possibility here is n5 is 1. So what does that mean is this n5 is basically normal. Not n5, let's say call this p5, which is the CeLO 5 subgroup. This is normal. Okay. Suppose if you have a normal subgroup, then what you can do is you can consider there is a map from G to automorphism of this P5. Okay, this map is in fact true in general. So I will write here maybe in the general statement. Suppose you have a normal subgroup of G. Okay, then you have a map here. Then there exists a homomorphism from G to automorphism of N. So how it is that you take a G and you map it into, let's say, 5G. Okay. So what is 5G? 5G is a map from N to N. It is automorphism, right? It's a map from N to N. It takes N here to Gn G inverse. Okay. So the definition, not to make this definition sense, this map well defined, you have to prove that G and G inverse must be in N, right? That is why you need the normality. If you need a normality, then you can have the G and G inverse actually belongs to N. And one can check that this is actually a homomorphism. Okay. So this homomorphism always exists as long as you have a normal subgroup here. In our case here, this P5 is what? The P5 is basically, this is isomorphic to it's a subgroup of order 5, right? So your group has order 15 here. So the CELO subgroup has what is the CELO subgroup order is basically 5. So this is automorphism of nothing but automorphism of Z mod 5Z. Okay. So what is Z mod 5Z? This is basically Z mod 4Z. Okay. So the automorphism of Z mod NZ is basically Z mod NZ star. And here you can observe that it's a group of order 4. Okay. And in basically it is equal to this one. This is easy to compute here. You can take it as exercise. It's easy to compute. Okay. So what happens here is here you have a okay, just give me a minute. Okay. So here you can get a map from this G also, but you can get a map from any H also here. See, once you have a map from G to this H, and if suppose this H is a subgroup of G, then there is always a map from H to the automorphism. How you take the H to G and then take it to automorphism. So you can get a, by composing, you can get a map from H to automorphism of N. Okay. So in this case, what we do is instead of this G, let me look at this subgroup here. So this is basically 3 times 5, right? So if I restrict this to P3, you will get a P3 means a CELO 3 subgroup. You get a map from here to automorphism of P5, which is isomorphic to Z mod 4Z. Okay. So, but this has order 3, right? And this has order 4. So what is this homomorphism? So there is only one such homomorphism possible, right? If you have a group from order 3 to order 4, there is only one such homomorphism. That homomorphism, it is trivial. Okay? Because you take any generator here, X here, and if it maps to some, let's say call this phi, okay, and you take phi of X. What you have to have is that phi of X order must divides 3. Okay, so the only element here whose order divides 3 is identity. So the only possibility is you map the generator to the identity. Okay. So thus, this phi is identity. Okay, what does phi identity means? Let's go here and see. This means this phi G is identity, right? That means this G and G inverse is basically equal to N. That is what it says. Okay, so G and G inverse is N. This map is identity means this group and this group commutes. So thus, so this means P3 and P5 commutes. Okay. So if these two groups commutes, and what is the intersection? P3 intersection P5. This is trivial, and this P5 is a normal subgroup again, right? So if you take a P3 times P5, so this is the group product. This will be your entire group because you compute the order here. If you compute the order of P3 times the order of P5, this is order of P3, order of P5 divided by order of P3 intersection P5. Okay, so this is 3 times 5 by 1. So this is basically 15. Okay, so this group, this is a subgroup of G, but it both has order 15. So this group is actually equal to this. So basically what we have is these two property, right? So with these two property, what does it tells you? It tells you that these groups are basically the same. So wait, I will tell. So this tells you G is isomorphic to G is isomorphic to P3 cross P5. So, or this is isomorphic to set 3 cross set 5. Okay. So this is the statement it tells. Okay, so basically what it tells is your group is actually abelian. If you have a group of order 15, then the group is actually abelian. So that comes because here, if you observe here, this map, the map of P3 going to the automorphism of a P5, this is actually identity. Okay, from here to here, how do we get it? If you want, probably I can prove it. If you already know it, it's fine. Otherwise, maybe I can prove some general statement. From that, it directly follows. Maybe I will write the general statement. You can keep it as exercise. It's very easy to do it if you. So, suppose, so I will write the statement. Maybe you can try to prove it. Keep it as exercise. If G equal to, let's say, Mn, and also assume M intersection N is trivial. Okay. Then G is isomorphic to G by M class G by M. I mean, basically, the M and N are normal subgroup, of course. Otherwise, this does not make sense. So maybe I will just write that also. If M comma N normal subgroup of G and G equal to Mn, G equal to Mn, and the intersection is 1, and then basically this is isomorphic to this. So basically what you do is you take the G here and map it into Gm, Gn, okay? Now you prove that this map is injective and, uh, just prove that this is injective and surjective. Then we can directly use the, basically what we prove is first to prove that the kernel of, let me call this as phi. Prove kernel of phi is identity. That is easy to prove. In fact, you can directly prove it. Kernel of phi is basically M10 intersection N, okay? And here we are assuming M intersection is N is 1. So this is equal to this. But try to prove that kernel of phi is basically M intersection N. Then a second statement is prove that phi is surjective. Okay. So here you need to use the fact that G is actually M cross N. Sorry, Mn. This you need to use the fact, use that particular fact, because if you choose any element here, any element if you choose here, that element looks like G1M comma G2N, right? But here you have to use the fact that G is basically Mn. So you will get G1 as M1N1, and you also get G2 as M2N2. Okay. Now what you do is you take this G as just give me 1 minute. Okay, so you have this, right? If you have this, you can also observe that G1M is nothing but N1M, okay? And also G2M, if you compute here, so G2N, this is nothing but M2N. Okay, because this M will go inside this M. Okay, so when you do the coset, these cosets are the same, because this M is a normal subgroup. So these two cosets basically are same. So from here you take the G as N1 M2. Okay, take G as let's say M2 N1. Then you compute. Let me call this map as phi, right? Compute phi of G. Okay, and to prove that this phi of G is basically Gm comma Gn. This will be basically N1M comma N2M. Okay, so this you need to prove it I'll just give the idea what you have to do, but there is some details that is left to be filled that you can easily fill it. Okay, so these are not easy. The kernel is you can easily compute. Okay, so this statement you will probably study in the ring theory also. This is called the Chinese remainder theorem, but in group theory also it is there. Uh, Ring theory, instead of the normal subgroup, there's some ideal or something will come, but let's not worry about that. So this theorem will be useful, so you can try to remember it. If you have a two normal subgroup of G, and if your group can be written as the product of this group, uh, then what you can write is you can write by M tensor n. You can write M intersection n is isomorphic to this. Okay, so this is the theorem. In particular, if this is equal to 1, then your group is isomorphic to this. Okay. Once you compute these two, use the so the third point is use first isomorphism theorem. Then you're done. Okay. Because the first isomorphism theorem says the G by kernel is isomorphic to the image, right? So what we have proved is kernel is 1, because here we have assumption, and this is subjective, so image is basically this. So that basically gives you that. So basically what you have to prove is this is the kernel, and the image is this. So for the image I gave an idea. Uh, See, this is the element of G by M cross G by M. Okay. This is the element of this, and you have to use that fact that G equal to M, otherwise you cannot directly get it. Once you use it, you can go like this. Okay, so what we have proved is there is no non-abelian group of order 15. Okay. So last time we had also, if you remember the last tutorial, what we did is we computed some classification for 15. We said that if the classification exists, then that is we gave one possible classification. I think I can directly show it here if you want. Give me a minute. Yeah, so this is a group of order 15, right? Yeah, so this is the last time we did. Assume G is a group of order 15. What we proved is the center of G is trivial, and there is at most one possible classification. So this we have proved last time, and that classification is basically here. So this is the possible classification. Okay, but what we proved today is this group does not exist at all. Okay.
Excuse me, sir.
Yeah.
Small doubt, sir. Group of order 15 is cyclic, no, sir?
Yeah, it is cyclic. Yeah.
Yes.
That means class equation should come 1 plus 1 plus all are 1 only, no, sir?
Yeah, that is true. That is true. Okay, I will show the problem here. So this is from last class, not from today. But what we proved is assume if there is a group of if there is a non-abelian group of order 15. So basically at that point we don't know. Let's assume we don't know. At that point we try to see if we randomly give you order, it is impossible to find because these groups are a small order, right? Here we can do something. But if you have a large enough order, it's almost impossible to find what are the possible groups of that order. So what we did is, suppose assume if there is an non-abelian group, then we proved that there is at most one possible classification. So that is what we proved. But in general, what happens is such a group cannot exist, as you said, because we just have proved it. There is a. So what we proved today here. Somewhere here. Yeah, so what we proved is there is no non-abelian group of order 15. That is what we have proved today. So any group here will looks like Z3, Z5, but you can see that if you take a element, let's say 1, 1, you try to compute it order will become 15. So these groups are all cyclic actually. Okay, and it's generated by 1, 1. like he have mentioned that this group is actually a cyclic group. So the possible classification is basically 1 plus 1 plus 1 plus etc. Okay. So in that sense, we can eliminate this one also. This is not correct. But what happens is, in general, if you look here, it's not easy to compute it's not easy to classify the groups. For example, these orders that I have written here, these are all classified, okay? But in general, it's not easy to kind of classify this kind of order. So whatever the techniques we are doing here, it's in some sense, we don't want to assume the classification. And then we want to the reason is that all the thing that we have did last time where we assume there is an non-abelian group, right? So what happened most of the time is before classification, how do you approach? So what you do is we assume, let's say there's a group and see what happens. So that is what we are trying to do. Although there are classification, we are not going to use the classification, and we just uh, we are trying to do it without the classification. So for example, here there is a classification. So here the groups has to be abelian, otherwise the group will looks like I can write it here.
It's
It will
D7.
it is a D7, but actually you can also write this as isomorphic to D2 semi-direct product, not D2, Z2 semi-direct product system. Okay, so there is this also you can write it as see 21 also you can write it as a Z3, I think, semi-direct product Z7. Okay, so there are certain here also you can write it as a Z3 semi-direct product Z13. But the semi-direct product we haven't done in the class. So if you are interested, you can look at the semi-direct product. Just for the interested person, I have just want to put the statement here. So direct product we have done in the class, but there is another notion called the semi-direct product. So if you look here, okay, maybe not here, but anyway, there is a notion called semi-direct product, and all these groups can be written as a semi-direct product. Okay, but this group does not exist. Other than this thing, everything can be written as a semi-direct product. Of course, this is D7, but D7 can as an isomorphic representation in terms of semi-direct product, and the group of order PQ is completely classified. Okay, so if you are interested, you can also look at groups of order PQ. So if any of you,
Sir, one more doubt, sir.
yeah.
So in last 7th assignment, first question is, if you know the class equation, we can determine it is abelian or cyclic, no sir? Both we can done, no sir?
Abelian we can determine.
Why not cyclic, sir?
See, if you have class equation, we can just say what is the center.
Now
right?
only you showed something, yeah.
So, for example, let me write there. So, let's say we have Z2 cross Z2. So, what is the class equation of this? So, this will be 1 plus 1 plus 1 plus 1, right?
Yes, sir.
You take Z4. What is the class equation of this?
1 plus 1 plus 1 plus 1.
So this does not, you have both, right? So basically, we cannot distinguish, cyclic or abelian. What we can prove is, you can prove it is abelian. If your classification looks like this, then it is abelian. You can prove.
But every cyclic group is abelian, no sir?
Every cyclic group is
I
abelian.
thought like that. I tick that answer, but it shows not correct.
Uh-huh. See, basically, you can say it is abelian or not, but you cannot say it is a cyclic or not. That is not possible. Because all cyclic groups are abelian, of course, but it does not tells you whether your group is cyclic. It tells you whether your group is abelian. See, for example, saying cyclic is in some sense more stronger than saying just abelian, right?
Okay.
Yeah, in that sense, it is more harder.
Thank you.
Okay, we can do some of this problem. For example, since we have discussed this, let's do this one. Okay, so this one will be easy, right? Anyway, this first problem was a little bit, it takes time, but once you get the idea, the rest of the thing we can do easily. I will just do some of these things, but rest I will leave it as exercise. Okay, so let's do it here. What about this one? This is not possible, right? Why? If you have a group of order 4, there's only two groups of order 4. One is basically, I will write here. So there is only two groups of order 4. Okay, just give me a minute. Yeah, there is only two group of order 4. One is this Z4 and another is Z2 cross Z2. So this is again kind of using the classification. Otherwise also we can prove it, but I'm not sure. Anyway, these small groups we anyway know the classification. Or maybe give me a minute. I probably try to prove. Maybe I can give a proof that these groups are abelian. At least that much I can give, I think. Yeah, maybe anyway. I don't want to try now. See, I just kind of assume the classification. I didn't done it, but we can directly, without using the classification, we can directly say this group is abelian and this is not coming. Anyway, but nonetheless, these groups are abelian. Group of till order 5, it is abelian. So this 2 is not possible. Okay, so this is not correct. So these are abelian. So the only classification possible is 1 plus 1 plus 1 plus 1. Okay. Okay, let's look at this particular one. Maybe I can do all of this, but I will just do 1 or 2 and leave the rest as probably exercise. Or maybe we'll do the 10 here. So this one you can work it out. There are only two groups here, S3 and D6, not D6, but basically people write D2 times 3. Sorry, that is also same anyway. Z6. Yeah, only these two groups are here. So this you try to compute here. For Z6, what you get is you will get 1 plus 1 6 times, and S3 you will get this classification. Okay, probably we do the group of order 10 and see among these 4, this I think I have written 5. Among these 5, which are the class equations? Okay, first of all, you can observe that this is the possible class equation, and the group is maybe possibly you can take a set 10. Okay, you take a cyclic group or abelian group. This is the only abelian group of order 10, and for that abelian group, this classification is possible. Okay. Now what we do is we'll compute what are the other possibilities, and maybe I will leave these things as exercise. Of course, I can do all of this, but the time is not there. These groups are probably smaller group we can easily compute. So I will just leave as exercise. We'll do 10 one time, and then probably we'll move on to next one. Okay, so maybe I will start here. Okay, so the idea of doing this is you can get used to how to use these Silo theorems as well as some classification. So you will not find it hard. Like the problem is the classification is not hard, but the first time when you see it, you feel like it looks hard. So probably we'll do some more problem here so that it will be easier to understand. Okay, let's assume your group has order 10. Okay. And also we can moreover assume that this is non-abelian. Okay. And before going any further, I will directly tell you, if it is a non-abelian group, there is only one such group is possible. Okay, and that is 2 times 5. I think so. I think this is the only group that may be possible. Possibly. But nonetheless, I'm not going to use this classification. Okay, so this classification is there, but I'm not going to use the classification. So what we want to do right now is rather than using the classification, etc., we will try to take an easy example and apply these Silo theorems and other properties that we have. So in that sense, we can able to use it later if we get a sense. Okay. So now let's look at N2. So N2 is what? The number of Silo 2 subgroup. Okay, so this is Silo 2 subgroup. So what we know is N2 is congruent to 1 mod 2 and N2 must divides 10. Right. Okay, so N2 is congruent to 1 mod 2. From here, what we can observe? N2 is either 1, 3, 5. I think 1 mod 2 is basically odd numbers, 9, 11, etc. And but it has to divide 10. So only possibilities is N2 is either 1, 2, sorry, 1 or 5. 1 or 5. Right, so these are the only possibilities. So what about N5? So here also you can use the Silo third theorem, or we can use the other thing that what you can observe is, so what, let's say take Silo 5 subgroup, okay? Let me call that as P. So if you look at index GP, and this will be 2, right? So this is a group of index 2, and 2 is the smallest prime that divides the order of the group, right? So any group of order 2 is, sorry, any group of index 2 is basically normal. So for the people who joined just now, I probably mentioned the theorem one more time. Maybe I don't want to say it again and again, because the ones who are already there, I have already told many times. But just for the other people, what the theorem we use is, if let's say your cardinality of G is N, and if you have any doubts, you can ask me. Doubts or comments, if you have anything, feel free to say. And suppose P is the smallest prime dividing N, then any subgroup of index N is normal. Is normal. Okay, so this is what we are using here. You take a Silo 5 subgroup and it has index 2, and this is the smallest prime that divides the group G, so this has to be normal. Okay, so this is normal means the NP is basically 1, N5 is 1. Why? Because the Silo second theorem says that any Silo subgroups are conjugates, right? The Silo second theorem says if you take any two Silo subgroup, P and Q, what the Silo second theorem says is they are conjugate. Sorry, if you take any other Silo 5 subgroup, by the second theorem, we have this is a conjugate, but this is a normal subgroup, so this is equal to P. So basically, this Q and P are same. So N5 is 1. Okay, so far what we have computed is N2 is basically equal to 1 or 5, or and N5 is 1. Okay, and again draw the diagram here. You have identity here, and you have N5 is 1, right? So basically, you have 4 elements here. Other than 4 elements, so basically here there are 5 elements. every other element has to, because we are assuming that your group is non-abelian, okay? So the other elements has to have a order 2, okay? And here if you have n2 is 1, then that means there's only one element of order 2 there. If you have only one element of order 2, then if you add it, you will only get 6, but you need 10 elements, right? So that means that is not the case. You need so this is not correct because you are assuming that it's not abelian. So this is not correct. So this has to be the correct one. So there is a two CELO subgroups and each have one element. So basically there are 4 elements. So basically there are 5 elements of order 2 here. So this is how your group is there now. So this is identity. Of course, this I don't have to worry about that. There are 4 elements of order 5, and there are 5 elements of order 2. Now again we do the same thing. So basically what happens is these groups are all group of order PQ, right? So the computation kind of goes similarly. If you take different groups, the computation will be different. But on the other hand, the different groups are more harder also. So tomorrow, I think not tomorrow, Tuesday we have another class, right? That time we will do a lot of thing that uses the zero subgroups. We'll say, okay, which are subgroups are simple, etc. We'll do some examples. But today we'll just do this one. Okay, again do the same thing, compute the centralizer. So let's say x has order 2. Now what you do is you have this x is contained in centralizer g of x. So your possible order for the centralizer is again 1, 2, 5 or 10. 10 is not possible because if 10 is the case, then this x will be in the center, just like what we have done earlier. So this is not possible. Okay, so but then from here, this is this subgroup generated by this is a element here. So it is contained here. That means 2 divides this centralizer, right? Means 2 divides cardinality of the centralizer of x. So what does it tells you? It tells you there are only one possibility, that centralizer g of x is basically equal to 2. Okay, so if you look at g by centralizer g of x, that will be 5. Okay, so basically this 5 subgroups forms a single orbit here. So if you look here, this is different from the other one, because that other one, whatever this 3 elements here, there are 26 3 elements, and that forms a 2 equivalence classes, right, of 13 13 each. But here this 5 forms a single conjugacy class. Okay, and we have element of order 5 here. There are 4 elements of order 5. Do the same thing you compute when x is the order of x is 5. You compute the centralizer g of x. Do the exact same thing whatever we have did here. You can observe that the centralizer has order 5. Okay, because again the same thing, this x will be contained in centralizer, so 5 divides the order of centralizer, but the only possible order of this, so centralizer order has to be 5. Right, so if you compute g by centralizer, you will get a 2 here. Okay, so what happens here if you write down this class equation? So you have 2, so we have identity here, and we have 4 elements of elements of order order 5. There are 4 elements of order 5, and that divides into 2 conjugacy class, each of 2 elements there. And this 5 elements kind of remains the same. So these are order 2. So if you look at the class equation, it will be 1 plus 2 plus 2 plus 5. Okay, so remember this, and let's go on to check what are the possibility, and we'll strike out the rest. Okay, so here we are. So what we get, 1 plus Okay, this is none of this is correct actually. So what we got is 1 plus 2 plus 2 plus 5. Okay, so if you observe that, none of this is correct. This is not correct, this is not correct. It's correct, and this is not correct. Okay, so only two possibilities is either this or this one. Okay. So most of the time, this is how you do. If you want to compute the classification, most of the time, this is all you're going to do. Somehow, always find this CLS of groups that gives you some information. Okay. So in generally, these are the few tricks you have. Always find the CLS of groups that kind of gives you some information, and different times you might need to assume some of these are non-abelian. So assume some of this non-abelian that gives you some more information, and then always try to compute the center here. When you compute the center, these theorems are kind of useful. Okay, so this kind of theorems will be useful, so if possible we can use it. And after using this, try to compute the centralizer. This is one of the trick that is commonly used. But certain, you see, these groups are all simple, easy examples. If you have groups which are hard, in general, this is not going to be that simple. But you can try. Maybe sometimes it will be there, sometimes it may not be. Okay, so maybe if you take this example, I'm not going to completely compute, but I will just tell you some certain things. For example, here if you look, maybe here you can find it. Okay, here you do this, but you will not get exactly anything. So yeah, probably should I do it or not? Other than 2 elements, I have 6 elements, right? Yeah, maybe you can try this. These are not hard. Okay, so let me
Sir,
move on to, yeah.
a group of 8 means we can try for D4, no, sir?
There is a D4, there is a quaternion also.
Quaternion and D4, sir.
Yeah.
I tried before this. I got 1 plus 1 plus 2 plus 2 plus 2, sir. It comes
Yeah,
like
yeah, yeah. That is what you will get. This you will not get here. But
oh,
yeah, so what you do is you assume that it is non-abelian group and try to compute what it is.
okay.
So one thing is we can assume that the group is quaternion and the dihedral and you can compute. That is, because small groups, the classification is there. And if you want, I can give a reference where the small groups of, up to 30 or something, you can directly see the classification.
Yes,
And
sir.
up to I think 2000, there is a classification. It's in the gap. So probably if anybody is interested, I can tell you a little bit. Up to order 200, so 2000. So there is a software called Gap. Okay, so this is a group uh, algorithm and the program. Oh, okay, I should have written here. Okay, so there is a software here. It's an open source software. You can directly download it, and inside that, if you want to see how to work with this, there are documentation files available online. So look at the documentation file. If you know how to do the C or C++, some coding knowledge if you have, you can easily do it. You don't need to know completely. Even if without that, if you just look at the documentation, you can directly find like the codes what you have to do. You can find it in the website. So in this, there is something called a small group library. In which group of order up to I think 2000 is classified, and probably 3 power some 7 or 9 is classified. I'm not sure, I forgot the exponent, but it's like 3 power 9, 3 power 7. I think at least 7 is there. 5 power 7 and 7 power 7 or something. Some for small primes also it is classified. The small group library has this. 3, 5, 7 and 11 power something was there, but this exponent and this primes are actually small. Other than that, it's not known. I mean, the classification is not done. That's not much known, but up to group of order 2000, and there is some prime power groups you can check. Okay. Anyway, so those classification are there. If you are interested, you can look it up, or maybe if you work in this area, you can use it. Okay, but otherwise, you try to compute it as he said. The answer will be, this will not be a classification, and the answer will be 1 plus 1 plus 2 plus 2 plus 2. So this is the classification. So, but you try to compute it here. Okay, from here, let me move on. Let me skip some questions here, and I will move on to something that is not kind of introduced in the class, but I will just want to. There's a theorem, in fact, a very celebrated theorem. Since we haven't done it in the class, I just want to kind of tell the statement. I'm not going to prove. Proof is not easy. That's maybe one of the reason it's not done in the class. I think it is not done in the class. If it is done in the class, you can let me know. I have checked it and it was not there, so I assumed it's not done. Anyway, the theorem is basically called the fundamental theorem of a finite abelian group. So I write it for finite abelian group, but the theorem is there for finitely generated abelian group, not necessarily finite. Okay, so what the theorem basically do is basically classifies the uh, finite abelian groups. So not up to 2000 I have said there is a classification is there, and for small primes and small exponent there are some classification. Other than that, the classification is not there. But for finite abelian groups, it is classified. Okay, so this is the kind of the structure theorem. It's like the cyclic group. There is a structure theorem, right? This is a structure theorem. So the theorem says if G is a finite abelian groups, then two statement has to happen. There's the statement 1 and statement 2. So the statement 1 says then G is isomorphic to cyclic groups, direct product of cyclic groups. Okay, Zn1, Zn2 cross etc. Zns. Okay, well this N1, N2 etc. These are integers, and it has to satisfy certain condition. One is all these Nis or Nj's are all greater than or equal to 2. That means what? That means basically Z mod 1Z is what? This is identity, right? So basically we are not writing identity as one of the factor. Okay, all the factors are at least Z2 or more. See, you can also write something like this, right? But we are not writing like this. That is what the first statement says. The second statement says this Ni divides Ni plus 1. Okay. So, sorry, Ni plus 1 divides Ni. So basically, this Ns divides Ns plus 1, etc. So basically, this is the largest one, and the N2 divides N1, N3 divides N2, etc. Okay, so these are the two properties that it satisfies here. And what more you can say is this expression is in some sense unique. That is what the second statement says. The expression is unique. By uniqueness, what do you mean? If you can write G as isomorphic to some other direct product, and also this direct product satisfy this property A and B, this A and B. What is A? A tells you that all these MIs are actually greater than or equal to, sorry here. Yeah, it tells you all these MIs are greater than or equal to 2. Okay, and the B tells you this one divides the previous one. So basically M2 divides M1. So this is the big number here, and other things divides this one. Then what it tells you is this S here is equal to this U here. Okay, so this U and S are equal, and all this Mi terms here, right? And this Mi terms are equal to this Ni, and this happens for all I. So this Ni and this Mi here, these are all same. We will write here. So this and this, so these things are all same. Okay. So this is the fundamental theorem of finite abelian group. So basically all the abelian groups are basically direct product of cyclic groups. Okay. So now we know a lot of things about cyclic groups, right? So we know how its automorphism looks like. Okay, so one can actually compute the automorphism of abelian groups. So, but I'm not going to do it. But if you're interested, you can look at automorphism of abelian group. That's a full classification is there. So basically, the automorphism kind of splits. So if you have a automorphism of K cross H, and this will be basically automorphism of K cross. I think it will split, but otherwise there will be some more time will come here on us to check. But I don't remember. So, but you can check it easily. Just do you have any doubts? Okay, I assume that's no doubt. So what we do right now is let's assume this theorem. Okay, we are not going to prove it. The proof is not uh, easy in the sense it takes some time. Okay, it's lengthy also. It's 2-3 pages proof. We are not going to prove it. And even I have only seen the proof only once, and I don't know it completely also. Completely means I have studied long before, and now I don't even remember. But what is important is actually this particular statement. Okay, proof if you see once it is fine. Maybe you will forget. That is okay. But this you can actually prove in much general setup. There is something if you study the commutative algebra in module theory. There is a you can study it in much general setup. Okay. So most of the time the proof will be skipped till you study the commutative algebra, and there's something called modules over PED. There you can just prove it directly. Okay, and as a corollary you will get this theorem, but I think you can find it in the book, the proof, if you are interested. But it will be lengthy, but we are not interested in that. But what we will do is we assume the theorem and let's do some some examples. Let's give a order and then compute. Okay, what are the possible groups of that order? So let's start with small order groups. Let's start with the order of G is 4. Okay, maybe try to remember this part only. So what you do is you're writing it like this, direct product of this. Only thing is this numbers satisfy this condition. All of these are greater than or equal to 2, and this divides this one, and this divides this one, etc. So this direction, ns divide ns minus 1, and etc. you have to do. That's all. Okay, and again another one thing is the order has to match, right? So that is all we are going to do. So if you take 4, what are the possibility? So I can write it as a Z4. I can write it as a Z2 cross Z2. Okay, so these are the only two possibility. Here we are also going to use the Lagrange theorem. Okay, so there cannot the other numbers cannot come. Only possible number is 1, 2, or 4. But see, 1 we are not going to use it. Okay, so only the NIs has to be greater than or equal to 2, right? So 1 we will not use. Okay, so let me compute one more example. Let's compute 8. Cardinality of G is 8. We are only looking at abelian groups, not non-abelian groups. Okay, so this is possibility. Another one is you can take a Z4 cross Z4. Okay. So what are the possible NAs? NAs can be either 2, 4, or 8, right? So that's what we are going to do here. And this is 2, sir, not 2. This is 4. So because what we know is this one has to divide this one, right? And similarly you have to do. So we are keeping this numbers a large number. And we're doing it. Okay, so this can be Z2 cross Z2. This is one possibility. Another possibility is Z2 cross Z2. Okay. And if you little bit observe here, just give me a minute. Did I miss anything? I'm just wondering. Okay, this is not possibility, right? When I want to write 8, I'm writing 16, so this is not possibility. Okay, I think these are the only possibilities. Okay, so this is how you kind of do it, and probably let me write another example. Maybe g equal to 2 square times, let's say, 5. Okay, so this is how you write. What is 2 square anyway? It's 4, 5, 20, right? So if you want to write everything, you can write it as Z20. You can write it as Z10 cross Z2. You can write it as what other thing you have? Okay, these are the only two things I think. Yeah, so these are the only two things. Because you see, one can also think I may miss a few, I'm not sure, but one can think that I can write like this, right? Z2 cross Z2 cross Z2. But you see, what the theorem says is this number has to divide this, right? So 2 has to divide, that is not possible. So I have to join these two things together. And that gives me Z10. Because you see, this if you take a Z5 cross Z2, this is basically Z10. So you can prove that this is cyclic. Okay, so this is how we write. These two groups are isomorphic, but when you write the fundamental theorem, this is what you take. This is not what you take. Okay. Okay, so these are the only two. Just wants to confirm that I didn't miss anything, but more or less I didn't miss anything. Okay, anyway, so this is how you write all the abelian groups. If you want, you can write all the abelian groups. So in that sense, abelian group is listed, and this theorem, at least the name you remember. If you even forget the statement, you can look it up. It's called the fundamental theorem of finite abelian group. Okay. Okay, so let's maybe move on to a few more simple examples, and probably we'll stop after that. Okay, maybe we'll do this one. These are all, these are not hard, but these are again simple examples here. So maybe one of you try, because 3 people are there, right? Let's see if anybody get the answer quickly. So what you have is you have a group of order 77. Okay. So the question is then what I can say about the center of this group is. So the question is the center of this group is isomorphic to either a Z mod 7Z, Z mod 11Z, Z mod 77Z, or just identity. So these are the all 4 possibilities. I just gave all the 4 of them.
So Z mod 77 is it?
Yeah, you're right. Okay. Can you explain why?
So because 77 is a cyclic group, sir. So center of the cyclic group is a whole group only. So and Z by 77 mod 77 usually is isomorphic to Z 77.
Okay. So
Is it okay, sir? Any other?
yeah, I mean it is okay for this problem. It is okay. Suppose if I give you a group of order, let's say just give me 1 minute. I will give one example. I will give a number. 21 I can give. Yeah, suppose if I give you a group of order 21, then I will ask you the same question. What are the possible, here I change the question, what are the possible centers? 7Z, Z mod 3Z, Z mod 21Z, on 1. So what are the possible orders here? I have a, I mean, what are the possible order for center? The same question.
21. Okay. So 21 is one cyclic on one non-abelian possible, sir.
Okay, okay. But in this case, how do you know? Here, there's no non-abelian possible.
Yes, sir, because 7 does not divide 11 minus 1. PQ form, no, sir. PQ form.
Okay, okay. Is it done in the class? Group of order PQ?
No, sir, I learned this earlier, sir.
Okay, okay, okay. Okay.
Yes, sir.
Okay, in this case, it is there.
Yeah, Z by 21 is it for cyclic, okay, sir, but non-abelian.
Yeah. Yeah, so there is two possibilities here.
Yes.
So anyway, so what he is trying to do is he knows a little bit more. So there is a classification of this group of order PQ. Okay, so this group of order PQ, if you look, there is a classification. So what it tells you, if let's say P is smaller than Q, okay, we assume here. If P divides Q minus 1, then there is two groups possible. One is, Z PQ. Another one is basically this group, ZP semi-direct product ZQ. Okay, and if P does not divides Q minus 1, then the only possibility is ZPQ. Okay, so there is a classification he is trying to use that. He is using that. So this group is a non-abelian group. You can prove it. And anyway, I'm not explaining what is this particular term, but you just assume there's a non-abelian group. And it's called semi-direct product. Those who are interested, you can look it up. It's a very important construction. Later on, you will find it very useful. So interested people can look it up. So he's using that classification. Okay. So what we probably prove right now, anyway, but we, since for those who doesn't know the classification, we'll just do the problem here. Try to without use the classification, okay? But we do the same thing again. Without use the classification, let's try to do it. So by Lagrange theorem, what are the, let me do for this particular one. Okay. For Lagrange theorem, what are the possible order? So you are working with your group order is actually 77. And by Lagrange, what are the possible order for center? And by the way, you are using classification, right? It is nice. In some sense, see, if you're going for, let's say, CSAR exam or something, most of the time, only this kind of groups will be asked. So if any of you are interested in CSAR, try to, do this classification because it will be useful. So this kind of groups they're asking. And if you look here, all of these questions that I put here in here, what is this? Yeah, most of these things I just take it from some net exam questions. Okay. Anyway, ideally I shouldn't say it, but anyway I said it. So for those kind of questions, if your aim is to kind of do it, then of course you can use the classification and you can do it. But in general, if I gave you some hard number here, you cannot directly use the classification and you cannot do it. So, but what we are trying to do is we avoid the classification as much as possible. So we can do it in some sense. We just try to learn the techniques, so we can use it for other groups if necessary. Okay, so we will don't use the classification and try to prove it here. Okay. So, but if you know the classification, it makes your life easy. That is good if you know it. Okay, so let's compute the center. The center is either 1, 7, 11 or the 77, right? So now again we go with the same thing. If G by center is if center is 7, let's say, if center of G is either 7 or 11, then G by center, if you look, this has order 11 or 7. So if it is a 7, then you get a G by center 11. If it is 11, G by center is 7. Okay. In both cases, what happens is G by center has to be this. G by center is cyclic. implies G is abelian. So G is abelian means center of G is basically G, and hence the order is 77. So this gives you a contradiction. So this 2 is not possible, because here you assume that the center of G is 7, but it tells you center of G is 77. So basically this is not possible. This 2 is not possible. So we can strike it out. So what remains is either 1 or 77. Okay. So if your center is 1, then such a group needs to be abelian, right? So if center of G is 1, then G is abelian. But basically what you can prove is, so maybe I will write the theorem here. Okay. If your group G has order, let's say PQ, and P is, let's say, less than Q. Without loss of generality, I can always assume P is less than Q. Okay. And suppose P does not divides Q minus 1, then there is no non-abelian group of order PQ. Okay, one can ask me, okay, how do I write the proof? Proof is exactly like this case. See, here I proved for the 15, right? See, here I proved for 15, right? Here you observe here. So this is P and this is Q, and here you can observe that P does not divide Q minus 1, which is actually 4. So 3 does not divide 4. So take this proof and just and then write, instead of 3 write P, instead of Q write 5. The same proof, just do mutandis, like just change it appropriately, you will get the proof for the other statement that we have written here. Basically the same thing you have to do here. You go for the automorphism. Okay, in general, if you look at automorphism of Z mod QZ, okay, if you look at the automorphism of this automorphism will become Z mod Q minus 1Z. Okay, and if your P does not divide Q minus 1, then this morphism will become identity. Okay, and you do the same thing as what we have did here. Okay, that will give you the proof.
Sir, excuse me, sir. Sir,
Yeah.
can you explain what is automorphism? That I'm having some doubt on that.
What do you want?
Yeah. Automorphism of P5 is isomorph to this one. How do we calculate that one? That is, I have doubts, sir.
Okay, maybe I'll calculate it here.
Yes.
Okay, see, this itself is known actually. Z mod NZ, if you look at the automorphism of this itself is known. Okay, but right now I don't remember what is the statement. If you remember the statement, it's not hard to prove. I have some idea what is the statement. I think basically what you have to do is you have to write it in terms of I mean, you just have to write it in terms of the prime power, and then you have to take something. But I don't remember right now for this. So I will probably skip this. I will just write probably for Z mod PZ. Maybe I can tell you what is the automorphism. So this is basically Z mod P minus 1Z. Okay. So this is isomorphic to this. But again, I have to say that proof, I am not sure if I remember the proof. I will try here, but again, I have to say that I don't remember the proof. This is equal, I know. But see, here the problem is, I'm saying this is a cyclic, right? That is not easy. I am not sure this is easy. This involves some number theory. So that part I don't remember exactly. Group theory part I remember, but number theory part I don't exactly remember.
Okay, sir. Okay, thank you.
So maybe what I can prove, I can probably do is I will prove this is the order is actually P minus 1. Maybe this is easy to prove, and this is enough for our purpose all our purposes, this is enough, right? So maybe I'll change here. Probably I'll just prove this one. This much is enough for our purposes. Whether it's cyclic or not doesn't really matter for us. So I will just maybe prove this one. This is easy to prove. So what you do is in Z mod QZ. So what you do is you give a automorphism here. Z mod QZ. Okay. What you do is you take one here. One is a generator, right? And maybe you call this a phi alpha. Take this one and map it into alpha times 1, or maybe not alpha times 1, 1 plus 1 plus 1 alpha times. Okay. Or in other words, if you want to write, I will just say this is a map 1 to alpha. Okay. And you can prove this is a automorphism. Okay. Prove phi alpha is automorphism. Okay, so it is not very hard to prove. What you basically you just have to use the fact that if alpha is not equal to 0, then alpha has an inverse, right? So inverse mod p, and this is what you are going to use. And once you use that, you can prove it. So okay, maybe what you can do is see, this is clearly okay. Maybe I will prove it here also. Directly I will prove it. So first of all, observe that this is a homomorphism, right? Because it's a cyclic group. Wherever I map the generator, once I map the generator, I have a homomorphism. Okay. So phi alpha is a homomorphism. So that is clear because this is a generator and I'm mapping this to some generator. Okay. So now I'm going to I need to prove this is a automorphism, right? So basically I have to prove it's a bijective. Instead of proving it's a bijective, what I'm going to do is I will just give you an inverse function. Okay. So I'm give the inverse function. So from here you can observe if you take a x, any x, this x will goes to alpha dot x. Okay, so alpha dot x is basically alpha times alpha times alpha, but that is the same as sorry, not x times x alpha times, but this is basically alpha times x, but this multiplication is modular multiplication. Okay, so here you can give a inverse here. So this is again a function from z mod 9z to z mod 9z. So what you do is you take again do the same thing, take 1 to alpha inverse. So this you can give because since alpha is not equal to 0, you can have an inverse for this alpha. Okay, and again this is again a homomorphism. And you just to prove that these are inverses of each other. Just compose it and see that this is identity, and do the other composition also. This is easy to compute. So this part I will leave it as exercise. You will just try it. It will come very quickly. So proving that this has this order is easy, and also proving that automorphism of z mod nz. If you look here, this has order phi of n. This is also easy. Proving this much is easy. But how this group looks like, it looks like it's a cyclic group. But that part I don't remember the proof. That uses some number theory, and I don't remember it right now. We have done it once in the Galois theory course, but I don't remember.
Yes, sir. Thank you, sir.
Yeah, okay. Okay, it's almost 2 hours probably, so I will stop. But I'll just look if there is any interesting question I have, then we can do. Or maybe I will upload the notes by tonight. So you can try this two problems as kind of exercise. Okay, we'll leave it as exercise. This is not a hard problem, but I'll just okay, and probably I will just leave these two problems as exercise. Since it's 2 hours, I will stop. But what we really did today is basically we did little bit of class equations. Okay, so the idea is okay, if we have it, how to use the silo subgroups, silo theorems to get uh, to see which are the following can be a class equation. Okay, so some of this I left you as an exercise. You try to compute it here, and I have told you some idea, but these things are all possibles. Okay, so again, I will just tell, because we have done some group of order PQ. I will just finish that also a little bit. Give me 1 minute. Sorry for, I think I have gone here and there, but I'm sorry about that. See, this is a classification group of order PQ. We have said, right? What we said is if P divides Q minus 1, then that is a 2 subgroup here. I mean, anyway, the cyclic group is anyway there. Cyclic group is there because if you look at this one, see, this is the only abelian group possible. Okay, use the fundamental theorem of abelian group. You can prove that this is the only abelian group possible. Okay, and the question is whether the non-abelian group exists or not. Okay, if P divides Q minus 1, there is a non-abelian group exists, and that non-abelian group, if I want to say some group exists, I have to construct it, right? That construction uses something called the semi-direct product. But which I'm not going to do it anyway. So if you're interested, you can look it up. If you want a reference, I can give. Look at the book by Damit and Foote. I think abstract algebra its name is. It's a nice book actually. There are very good problems. If you're interested in solving the problem, you can look it up. Okay. So look at the semi-direct product section, this construction is there. And what we have proved is if P does not divide Q minus 1, we have proved that there is no subgroup of order, no non-abelian group. This part we have proved, this part we have proved, but the non-abelian group, there is a construction and we have to prove there is a unique non-abelian group, right? Those two part remains, and that if you are interested, you can look here. If you give me 1 minute, I can even tell you the page number. List the page number of the semi-direct product I can give you. So the exact page number, it's basically section 5.5. Okay, page number 181. Okay, so if you're interested, you can look here. He has so many examples. So for example, group of order 30 is classified and other things are classified. If you're interested, you can look it up. Okay, I will stop now, but if you have any doubts in the tutorial or something, you can ask me now.